Hello everyone. In this video, I will be explaining orthogonal property of Bessel function. If you are watching my video first time or if you have not subscribed my channel yet, subscribe this channel and also press the bell button to get more updates of the videos which I'm going to upload here. Now, we will move to the concept of orthogonal property of Bessel function. So we have Bessel's differential equation x square d square y by dx square plus x dy by dx plus lambda square x square minus n square of y equal to 0. This type of special differential equation, we call it as Bessel's differential equation. It has solution of the form Jn of lambda x. The solution of Bessel's differential equation we have derived in the previous videos, and we have denoted it as Jn of lambda x. Now let u equal to Jn of alpha x and v equal to Jn of beta x. Suppose this equation number 1 is the Bessel's differential equation, then its solution is Jn of lambda x. Now we consider, instead of lambda, we considered alpha and beta. Similarly, the notation also u and v. So then the corresponding Bessel's differential equations are x square u double dash. U double dash means d square u by dx square plus x du by dx, that is u dash, plus alpha square x square minus n square into u equal to 0. Let it as equation number 1. Similarly, second one, x square v double dash plus xv dash plus beta square x square minus n square of v equal to 0. Give it as equation number 2. Now, multiplying equation number 1 by v by x and equation number 2 by u by x. Let us see what happens. If you multiply v by x to the first term of first equation, that is x square u double dash into v by x. So one x from the denominator cancel, v remains in the numerator, x remains, u double dash remains. That is, this will be x into v into u double dash. Similarly, if you multiply v by x here, so x cancel, remaining expression will be v u dash. Similarly, if you open the bracket and multiply v by x to the first term, so alpha square v x will remains into u, that is alpha square uvx will remains, one x from the denominator cancel, minus n square u. If you multiply v by x, this will be minus n square uv by x equal to 0. Let us see that expressions. That is x vu double dash plus vu dash plus alpha square uv dash uvx minus n square uv by x equal to 0. This is after multiplying v by x to equation number 1. Similarly, if you multiply u by x to equation number 2, we get x uv double dash plus uv dash plus b square uvx minus n square uv by x equal to 0. Now, what happens if you subtract these two equations? First term minus first term of these two equations, that is xvu double dash minus xuv double dash. So x will be common and vu double dash minus uv double dash will be there. Vu dash minus uv dash will be there. Alpha square uvx minus beta square uvx. Uvx will be common. And last term, that is minus n square uv by x, will cancel with the minus n square uv by x when you subtract. So that we see. So on subtracting both of the above equations, we get x into vu double dash minus uv double dash plus vu dash minus uv dash plus alpha square minus beta square uvx equal to 0. This we can write it as d by dx of x vu dash minus uv dash equal to beta square minus alpha square of x uv. Here alpha square minus beta square is shifted to right side. So this becomes beta square minus alpha square. Now, how did we relate this x into vu double dash minus uv double dash plus vu dash minus uv dash with d by dx of x into vu dash minus uv dash? This we just thinking in the reverse order of the differentiation. We have answer of derivative term here. We just written in d by dx, that is in the function form. That we can verify by finding d by dx of x into vu dash minus uv dash. So we see what is this answer. Here we have to apply the product rule of differentiation, because x is first function, vu dash minus uv dash is the second function. First function into, that is x into derivative of second, that is vu dash minus uv dash. So again you have to apply the product rule while finding derivative of vu dash and while finding derivative of uv dash, that is vu double dash plus u dash v dash minus vu uv double dash minus u dash v dash plus vu dash minus uv dash, which can be written x into vu double dash minus uv double dash plus vu dash minus uv dash equal to, or on integration, this is the reason why we wrote as d by dx of this expression. Now next step, on integration both sides from 0 to 1, that is integrating both sides 0 to 1, we see what happens. 0 to 1 integral d by dx of function equal to 0 to integral 0 to 1 beta square minus alpha square x uv dx. We know that integration and differentiation are inverse process. So here integration and differentiation will eliminate and function will remain. That is x into uv dash minus vu dash. Since integration from limit 0 to 1, here for the function we have to give the limit from 0 to 1 equal to, being beta square minus alpha square constant we take outside, into integral 0 to 1 x uv dx. So we apply the upper limit and lower limit left side. Upper limit x is 1 means 1 into vu dash minus uv dash at x equal to 1. Here I have written x equal to 1 because we don't know what is v and u or u dash and v dash. So just we write x at x equal to 1 minus 0, because here 0 into anything will be 0. So minus 0 for lower limit equal to beta square minus alpha square integral 0 to 1 x uv dx. Let it as equation number 3. Now we have u equal to jn of alpha x, which means u dash derivative is equal to jn dash of alpha x, alpha into jn dash of alpha x, being alpha is constant. Similarly, v equal to jn of beta x implies v dash equal to beta into jn dash of beta x. Then this we substitute in equation number 3. That is, this is our equation number 3. Here we substitute in the place of v, we substitute jn of beta x. In the place of u dash, we substitute alpha into jn dash of alpha x minus In the place of u, we substitute jn of alpha x. In the place of v dash, we substitute beta into jn dash of beta x. Similarly, in the right side also, in the place of uv, we substitute it, we get this expression. And left side x equal to 1, because we have not substituted for x equal to 1 in the functions. Right side, beta square minus alpha square, integration from 0 to 1, x jn of alpha x into jn of beta x dx. This means we can also write integral 0 to 1 x jn of alpha x into jn of beta x dx equal to beta square minus alpha square. From the right side, we are shifting to left, so we get 1 by beta square minus alpha square into alpha into jn of beta into jn dash of alpha, because we are putting x equal to 1, so beta x becomes beta, alpha x becomes alpha, minus beta into jn of alpha into jn dash of beta. So this is what this integral. So give it as equation number 4. And we also know that alpha and beta are distinct roots of jn of x equal to 0, which means jn of alpha is 0 and jn of beta equal to 0. So by this, equation 4 will becomes, wherever we see jn of alpha and wherever you see jn of beta, we put it as 0. So we get integral 0 to 1 x jn of alpha x into jn of beta x dx equal to, right side full it is 0, because here we have jn of beta and here we have jn of alpha, both 0. So 0 into anything is 0. So equal to 0. Provided beta square minus alpha square should not equal to 0. That means beta square not equal to alpha square. That means beta not equal to alpha, because in equation 4, right hand side, we have 1 by beta square minus alpha square. We have to see that denominator term should not 0. That is possible whenever alpha and beta are distinct. Now, thus when alpha not equal to beta, we conclude that integral 0 to 1 x into jn of alpha x jn of beta x dx equal to 0. Now we have to discuss a particular case, that is what happens j alpha equal to beta. So RHS of equation 4 becomes 0 when alpha equal to beta. So we cannot evaluate this one. So this becomes an indeterminate form of the type 0 by 0 when alpha equal to beta. So hence we apply L'Hospital's rule by taking beta tends to alpha and keeping alpha fixed. So we are applying limit now and also L'Hospital rules. So if you apply the limit left side, limit beta tending to alpha, integral 0 to 1 x jn of alpha x into jn of beta x dx equal to, right side applying limit beta tending to alpha 1 by beta square minus alpha square into alpha jn of beta jn dash of alpha minus beta jn of alpha into jn dash of beta. Here alpha is fixed and it is root of jn of alpha x equal jn of x equal to 0. Therefore jn of alpha is 0. We assumed alpha is fixed and constant. So therefore jn of alpha will be 0. So in the right side we have jn of alpha, so that we will substitute as 0. And also we will put the limit in the right side by applying L'Hospital rule. L'Hospital rule, whenever 0 by 0 form is there, so we have to differentiate numerator, that is alpha into jn of beta into jn dash of alpha. This we have to differentiate numerator. Here beta is tending to alpha, beta is variable, so derivative of Jn of beta we have to write, and denominator beta square minus alpha square we have to differentiate with respect to beta, as beta is variable. So we get left side equal to limit beta tending to alpha 1 by beta square minus alpha square, alpha into Jn of beta, Jn dash of alpha. El Hospital rule we will apply in the next step. So here we just substituted for Jn of alpha is 0. In the next step we will apply the El Hospital rule. That is one limit beta is tending to alpha 1 by 2 beta, because derivative of beta square minus alpha square is 2 beta into alpha into Jn dash of beta into Jn dash of alpha. So now integral 0 to 1 Jn of alpha x into Jn of alpha x, because we applied limit beta is tending to alpha. So beta we replace by alpha, equal to 1 by 2 alpha, because after differentiating numerator and denominator separately according to El Hospital rule, we have to apply the limit. So denominator beta replaces alpha, numerator alpha into Jn dash of alpha, because beta replaced by alpha, Jn dash of alpha, which means integral 0 to 1 x Jn square alpha x dx equal to 1 by 2 Jn dash of alpha whole square. This is the case when alpha equal to beta. So this is the property, orthogonal property.